Hola amigos, let's start with Elements of Airplane Performance, chapter 6 at page number 385, and these are the topics. Around 100 plus pages are here, and we have left around 7 topics from the book of Introduction to Flight, which we are following by J.D. Anderson, 6th edition and Special Indian edition. And these topics will be covered one by one, and let's first see unit conversion and standard values, which I will be sharing every start of the chapter. Earlier also I have shared, so please pause the video and note these down. And let's start Elements of Airplane Performance. So first topic we have is drag polar, and drag polar shows the significant curve, a very important graph which is between CL and CD. It's parabolic. CD varies parabolically with CL. Drag polar is the curve that tells us about the variation of drag coefficient with the lift coefficient, and in this we get to know about the minimum drag or minimum drag coefficient or the induced drag coefficient, or say the drag at zero lift, which is here, is the minimum drag coefficient. CD naught is the drag coefficient at zero lift, because lift is 0 over here, over this axis CL is 0, so CD naught will be coefficient of drag at zero lift, and it is the minimum drag. If we take this curve, this is the minimum point, which is the minimum drag coefficient. So total drag coefficient of a plane is CD equals CD naught plus CDI, which is KCL square. And if we talk about highly compressible flows in which shocks occurs like hyperbolic speed or supersonic speeds, at that high Mach number, we have waves, shock waves, in which the airplane experiences wave drag. So in that case we will have, on addition with these two, we will have plus CDW. So we are only studying about subsonic flights, so we will have this CD equals CD naught plus CDI. So subsonic flights are basically Mach number less than 1, so we will stick to that only for the study of airplane performance. And in drag polar we have CD equals CD naught plus CDI, which is CDI equals to KCL square, and K is the constant, which is 1 by pi E aspect ratio, and CL we know coefficient of lift, CD naught minimum drag coefficient over here from this graph, and pi constant value, E is the Oswald efficiency. E is basically always less than 1 or equal to 1. It is equal to 1 for a wing with elliptical shape. Okay, if a wing is in elliptical shape, then E will be equal to 1, and for every other shape E will be less than 1. Basically, if you see the design of Spitfire airplane, you will see E for that will be equal to 1, because it's planform, or say if you observe the wing from the top, okay, if you say this is the wing and if you observe it from the top, and you will see the shape of the wing is elliptic, and for that E is equal to 1. And aspect ratio is the how the wing is designed or layout. Let's say the airplane is like this and we have wing like this. Okay, so the aspect ratio will be B square. B is the distance from this to this, from one tip to another tip is the distance of span, we say. B square divided by S. S is the planform area, the area that we see from the top will be the S. S is B times C. C is the width. Okay, if say the width of the airplane as you see it from the above is this much, and this much is the length C. B into C is S. So aspect ratio is B square by S. Okay, so with this we have drag polar CD equals CD naught plus KCL square, where CL square and K is given by 1 by pi E aspect ratio. And this we have as a preliminary design consideration. If we start to design an airplane, we basically use this as a standard graph. And if we talk about actual aircraft design, and when we analyze the CL CD curve, here CD CL curve we have, and if we mirror this, then we will see CL CD curve. And in that actual aircraft design, here it is preliminary, here we are talking about actual aircraft design, in that we will see that CD minimum is not equal to CD naught. CD naught is more than the CD minimum. So CD naught is all that drag acting on the aircraft, which is not because of the lift producing elements on the airplane. Lift producing elements are canards, wings, or say tail section, horizontal tail section. So whatever may be the drag produced by these lift producing parts, they will all come under this CDI range, induced drag range, and every other non-lifting drag component will come in CD naught. Parasite drag we call it. Parasite drag is all because of skin friction and pressure drag. Skin friction and pressure drag, which are not contributing to lift, comes under this CD naught, and every other lift producing element which take part in drag comes under this CDI. So basically you will learn this difference in that lift and drag are actually perpendicular to each other. If say lift is in vertical direction, drag is in horizontal direction, they should not be having a component in their directions. But it so happens that relatively the velocity field around the airplane wing changes such that the local flow field gets changed, which makes this vertical lift component tilt a little bit, which makes a component in the horizontal direction. And in the horizontal direction we have this velocity coming, and in the direction of velocity we have a horizontal component of lift, which is creating a drag on this aircraft in the horizontal direction. So drag in the horizontal direction because of lift is the induced drag. And with this we have, for an actual aircraft, we modify this drag polar equation CD equals CD minimum plus CL minus CL minimum drag whole square divided by pi e aspect ratio. So CL at CD minimum will be CL at minimum drag. Okay, so the shift over here is because CD naught is not the CD minimum drag, and it does not come at this this symmetric axis like this. It is a symmetric over here, and therefore over here for actual aircraft design there is a shift. And pressure drag at lift equal to 0 is greater than the pressure drag at alpha equals to 0. That is, let's say we know in general CL alpha curve for wing or an aircraft is like this. CL is varies like this. So at this negative angle of attack we have 0 lift, therefore coefficient of lift is 0, and at alpha at lift equals to 0 is this, which is negative, and the intercept at y-axis is 0 CL naught, which is lift coefficient at 0 angle of attack, and it reaches up to a maximum which is CL max and gives us the stall angle, alpha stall, at which it can orient itself at a maximum angle. If you say this is the aircraft, okay, and this is the maximum position, it can stay at without losing any lift drastically. So this point is here to state that it should maintain a lift coefficient of lift less than this alpha stall. Okay, it should fly at alpha less than alpha stall. It is the maximum angle of attack at which it should fly to create maximum CL max. Okay, and now coming back to this figure and relating it with this, we see that pressure drag at lift equals to 0. Here lift is equal to 0, and pressure drag, if we say for at lift equal to 0, is more than the pressure drag at alpha equals to 0. So alpha is 0 over here, and alpha at lift equal to 0 is there. So alpha at lift equal to 0, we can see from this graph, is negative. That is, our aircraft is a little banked, little tilted downwards. Sorry, not banked. The right term is orientation is downwards like this, and our aircraft is like this, and while the free stream velocity is coming like this, v infinity is like this. So the angle between this velocity and airplane is alpha at lift equal to 0, which is negative. And pressure in this situation, pressure drag will be more than the pressure drag when the v infinity, or say the velocity, is parallel to the airplane axis. Okay, so which means if velocity is parallel to the airplane axis, then alpha angle of attack will be 0. Okay, so keep this in mind, and we will start continue in the next lecture. Thank you.